So operators can be represented by square matrices, and its matrix elements are denoted as A double prime x A prime. This is bra A double prime x get A prime. There are n square numbers like this, and they go into the square matrix. Okay. Now we can also denote, we also said that we'll denote it sometimes like this, x A double prime A prime. And then we looked at matrix operator multiplications of the form z is equal to xy. And we saw that the matrix elements in this case can be represented as the multiplication of matrices. Okay. For example, we can write the A double prime A prime element of z as, you can write this as there's a sum over A triple prime, and then bra A double prime x get A triple prime, bra A triple prime y get A prime. Okay, this is the usual matrix multiplication rule. As we said, this can be, we wrote this in this instructive manner. We said this looks like z A double prime A prime is equal to sum over A triple prime. I've got x A double prime A triple prime and y A triple prime A prime. Okay, so this is the usual matrix multiplication. Okay. Now it's time to look at the relation. Okay, the other kind of relation we are interested in is the multiplication of an operator and a ket. The multiplication of an operator and a ket. Okay, so for example, let's look at the relation ket gamma is equal to x acting on ket alpha. Right, ket gamma is equal to x acting on ket alpha. How can we represent this using as a matrix multiplication, or can we represent this as a matrix multiplication? Okay. Now in the Euclidean, for example, the Euclidean 3-vector case, we said that we can represent a 3-vector by a column matrix. Okay, this column matrix is consisting of the, what do you say, the expansion coefficients, all right, the expansion coefficients. You could write as Vx, Vy, Vz, or alternatively as V1, V2, V3. Okay, so in the same way, we might be able to represent this multiplication as matrix multiplication. All right, so a matrix, a square matrix acting on a column matrix, giving you another column matrix. Right? So let's look at the expansion coefficients of the ket gamma. To find the expansion coefficients of ket gamma, you project it onto the basis. You project it onto the basis, right? And we have already chosen the basis as the set of eigenkets of an operator A, of a Hermitian operator A, right? So let's look at the expansion coefficients of this ket. So to find the expansion coefficients of this ket, you project it onto the base ket, right? So we see that bra A prime ket gamma, this is the expansion coefficient of gamma in the direction ket A prime, okay, in the direction of ket A prime. Now this becomes bra A prime x ket alpha. Right. Now again I can introduce an identity operator in here, so this becomes bra A prime x, right? So I'll insert an identity operator here, sum over A double prime ket A double prime, sorry, ket A double prime and bra A double prime, okay, and then I have got alpha here, right? So the summation, let me pull it out. So this is sum over A double prime. What I have here is bra A prime x ket A double prime and then bra A double prime ket alpha, okay. And what do I have on the left side? This is bra A prime ket gamma. Okay. Now again, this looks like a matrix multiplication. Right? Let's write it in this manner. Let's say that there's a matrix that represents the ket gamma, a column matrix that represents the ket gamma, and the elements are given by bra A prime ket gamma. Okay, let me just denote this as ket gamma A prime. All right, this is just for the sake of understanding. I'll denote this as gamma A prime. All right. So again, here ket gamma stands for ket and gamma A prime stands for the corresponding column matrix. Okay, we'll see that this is a column matrix. So this is equal to sum over A double prime. We said that this can already be denoted as x A prime A double prime. And this again, using this notation, can be written as alpha A double prime. Right? So this is a multiplication of a square matrix and a column matrix, and this is a column matrix. Right? This is exactly how we multiply a square matrix and a column matrix to get another column matrix. Right? So for example, let's take the matrix multiplication AX. Okay, this A and X are matrices. A is a square matrix. Suppose A is a square matrix and X is a column matrix. Okay, the resultant column matrix, the elements of the resultant column matrix can be written by the rule. Okay, let's say that this is Y, this is a column matrix Y. So we can write Yi is equal to Aij Xj. Now we have to sum this over J. Right. So this relation, right? So what I'm saying is that this relation looks like the multiplication of a square matrix with a column matrix if you arrange these numbers as a column matrix. So the idea is that these are numbers. We can arrange this as a column matrix. These numbers can be arranged as a column matrix. The C1, C2, C3, etc. The expansion coefficients, right? The expansion coefficients of a vector or the expansion coefficients of a ket in a given basis can be written as a column matrix. Right? And then we can write this relation as a matrix multiplication. So the matrix multiplication here is a square matrix acting on a column matrix giving another column matrix. All right. So this is the same as what we said in the Euclidean case. We can represent a vector by its expansion coefficients in a specific basis. Right? And if you change the basis, set, of course, these expansion coefficients also will change, and the same vector would be then represented by, let me be careful here, the same vector would then be represented by Vx prime, Vy prime, Vz prime. And we know that we can go from this set of components to this set of components by a rotation. Okay, so in much the same way, here we have a vector or a ket alpha, and we are saying that it's convenient, or we can actually represent it as a column matrix, right? What goes into this column matrix? The expansion coefficients of the ket in a given basis, right? The expansion coefficients of the ket in a given basis. Okay, right? So this can be seen as an application of the rule of multiplying a square matrix with a column matrix once the expansion coefficients of ket alpha and ket gamma are themselves arranged to form column matrices, right? So we can represent this ket alpha by this column matrix, okay? Column matrix consisting of the expansion coefficients in the chosen basis. Right, so ket alpha can be represented by this set of numbers. Ket gamma can be represented by this set of numbers. All right. What are these numbers? These are the expansion coefficients of gamma in the chosen basis. Right. So we have seen that we can represent operators as square matrices and kets as column matrices. Okay. Now we can also look at the relation between two bras. Okay, look at this relation. Bra gamma is equal to bra alpha acted upon by operator x. Okay. Now remember that you have to put the operator on the right of the bra. If we want to multiply a bra and an operator in a legal manner, the operator should come on the right of the bra. Okay, that's why we write bra gamma is equal to bra alpha x. So in order to find the corresponding matrix multiplication, we just multiply by ket a prime on the right. Okay, so this becomes bra alpha x ket a prime. All right. Now we can bring in the matrix elements of this operator, or the matrix representation of this operator, if we introduce an identity operator here. So let's introduce an identity operator here, which is written as sum over a double prime, ket a double prime, bra a double prime. Okay. So if I introduce this identity operator here, we get gamma bra gamma ket a prime is equal to, or bracket gamma a prime is equal to sum over a double prime. The summation sign I have pulled outside. So the rest of it is, we have got a bra alpha here, ket a double prime, and bra a double prime x ket a prime. Okay. Now this looks exactly like a multiplication between a row matrix and a square matrix. All right. So for example, we can write this is the rule for multiplication of a row matrix and a square matrix to get another row matrix. All right. So for example, we have got a row matrix like this, gamma a prime, and it is written as a multiplication between another row matrix, let's say alpha a double prime, and a square matrix x a double prime, x a double prime a prime, a square matrix with elements x a double prime a prime. Okay, so we need a summation here. All right, so this relation is like this, and this is the rule for a multiplication between a row matrix and a square matrix. Okay. This means that bras can be represented as row matrices. We have seen that kets can be represented as column matrices. Now bras can be represented as column matrices. And what are the elements of this column matrices? The elements of the column matrices are bracket gamma of the form bracket gamma a prime. Okay, so if you want to enumerate the elements, we can say that bra gamma can now be represented as a row matrix. And what are the elements of this row matrix? Bra gamma ket a1, okay, bra gamma ket a2, etc. Alright, so the elements in this row, the number of elements in the row matrix is equal to the number of basis vectors, number of base vectors. Okay. Now we can also write this bra gamma ket a1 is also equal to bra a1 ket gamma star. Okay, this is the basic rule that we have seen several times. If you interchange this, there's an extra complex conjugate, extra complex conjugation. So this means that bra gamma can be represented as a row matrix with elements bra a1 gamma star, bra a2 gamma star, etc. All right. So we see that we can represent bra by a row matrix and ket by a column matrix. All right. Now there's something else we can understand from here. There's something else that we can observe here. We said that ket gamma is represented by a column matrix with elements bra a1 ket gamma, bra a2 ket gamma, etc. All right. And we also see that bra gamma can be represented as, sorry, I should put this is represented by symbol here. So ket gamma is represented by a column matrix and bra gamma is represented by a column matrix of this form. What do I have the elements? What do I have for the elements? I have got ket a1 gamma star, sorry, bra a1 gamma star, bra a2 gamma star, etc. But you see that the elements here are the complex conjugate of the elements here. All right. So we have talked about this dual correspondence. We can go from the dual correspondence. We can go from a ket to a bra. Can go from a ket to a bra. All right. Now, if these are represented by matrices, column matrices, what's the rule from going from a ket to a bra? You see that if we transpose this thing, if we transpose the matrix that represents the ket and then complex conjugate it, we'll get the corresponding bra. Okay, we'll get the corresponding bra. So how do we go from the matrix that represents ket gamma to a matrix, to a row matrix that represents bra gamma? You take the matrix that represents ket gamma, transpose it and complex conjugate each element. So that will give you ket. So that will give you the matrix that represents bra gamma. Okay. All right. Now what about the inner product, bracket beta alpha? Right, this can be written as the product of a row matrix representing bra beta and a column matrix representing ket alpha. Right, when you multiply a row matrix by a column matrix, you'll get a number. So this inner product is a number. So our basic rules for inner product works with matrices also. Now how do we see that? Again, you introduce an identity in between, sum over a prime, bra a prime, sorry, ket a prime, bra a prime, and then ket alpha. Right, so the summation can be pulled out, sum over a prime. I've got bra beta ket a prime and bra a prime ket alpha. All right. Okay. Now this is clearly a multiplication between a row matrix and a column matrix. All right. So this sum over a prime, bra beta ket a prime, bra a prime ket alpha can be written as, you can get the elements of this. All right. So if you multiply this and add, all right, this what we'll get. So let's say that we'll get, let's do this summation, right? So that we'll get beta a1, okay, beta a1 alpha plus beta a2. I'm summing over a prime here. Okay, I'm summing over all this base kets and bras. Okay, so bra beta ket a2 multiplied by bra a2 ket alpha, etc. Okay, now this summation or this expression can clearly be obtained by by multiplying a row matrix and a column matrix. Okay, what's the row matrix that we need to look at? The row matrix can be written as bra beta a1, okay, bra beta a2, etc. Okay, and the column matrix can be written as bra a1 ket alpha, bra a2 ket alpha, etc. Okay, there will be n elements of this form. If I multiply this, okay, multiplying this matrix also will give us exactly the same expression. Okay, this means that the inner product beta alpha can now be represented by a multiplication of a row matrix and a column matrix. Okay, the elements of the row matrix can also be written as, this is bra beta ket a1. You can also write this as bra a1 ket beta star. Okay, similarly, this can be written as bra A2 ket beta star. Okay, so the inner product can be written as a product of a row matrix and a column matrix. Now, if we multiply the row matrix representing ket alpha with the column matrix representing, sorry, if we multiply the row matrix representing bra alpha with the column matrix representing ket beta, all right. So here we have found bra beta ket alpha. All right. We could also do bra alpha ket beta. Okay, and we can see that this is equal to bra beta ket alpha star. Okay, this is the fundamental rule for multiplication. Right. So I leave it as an exercise for you to check that this property is indeed satisfied. Okay, do the same thing. You find bra beta ket alpha in this manner. Okay, write the expression. Find bra alpha ket beta again by introducing an identity here and expand this expression like this. Okay, write a few terms and show that the second one is the complex conjugate of the first one. Okay, leave it as an exercise for you. Now let's look at the representation of the outer product ket beta bra alpha. Okay, we said that this is an operator, so its matrix elements can be written as, let's say, bra A1, bra A double prime, ket beta, this is ket alpha, ket A prime. Right, so I can find the matrix elements of this operator between two eigenstates, okay, or between two eigenkets for that matter. Right. Now this can be written as A double prime beta and then A prime alpha star, A prime alpha star. Okay, now you can enumerate all the elements like this. Okay, if we take the set of all eigenbras, we take the set of all eigenkets as we did for the operator x. So the elements are A1 beta, A1 alpha. Okay, this is bra A1 ket beta, bra A1 ket alpha star. Okay, so this is the first row, first column. What's the first row, second column? This is first row, second column element is bra A1 ket beta, bra A2 ket alpha star, etc. So this is just an example of the matrix representation of an operator that we saw before. Okay, all right. Now, if you are representing a ket by a column matrix, okay, and bra by a row matrix, so this can be obtained, all right. This square matrix can be obtained by a multiplication between a column matrix and a row matrix. All right, let me write it out. This square matrix can be obtained by multiplying a column matrix with a row matrix. What are the elements of this column matrix? The elements of the column matrix are this. Okay, because this is a ket, so the expansion coefficients of this ket are written like this. Let's write it as A1 beta, A2 beta, etc. Right, and these elements, right, here, these are bra alpha ket A prime, or we can write as bra A prime ket alpha star. So what are the elements here? This is bra A1 ket alpha, bra A2, sorry, there's a star there, and bra A2 ket alpha star, goes on like that. Okay, now if you multiply this, clearly we'll get a square matrix. How do I multiply these two matrices? First row multiplied by first column. So that is A1 beta A1 alpha star. Okay, now let's look at the first row multiplied by the second column. Okay, first row multiplied by second column, that will come here. Okay, what would be that element? This is bra A1 ket beta. Okay, and then I have got first element multiplied by the second row, first row multiplied by the second column. Here I have bra A2 ket alpha star. Okay, that's exactly the element that we have here. Okay, bra A1 ket beta, bra A2 ket alpha star. All right, so we are actually constructing what is a square matrix from a column matrix and a row matrix. Okay, so if I put the row matrix on the left side, it's a number. All right, if I put the row matrix on the right side of the column matrix, I have got a square matrix. Okay, we have said that if an operator A is Hermitian, we can take its eigenkets and use it as basis. Okay, use it as an orthonormal basis. Okay, the next question is, what happens if I represent an operator A in this basis? the basis formed by its own eigenkets. Okay, we know that once we have a basis, we can represent any operator as a square matrix in this particular basis. Okay, what happens if I choose to represent operator A in the basis formed by its own eigenkets? All right, so this makes the matrix representation of operator A rather simple. Let's see how. Okay, so we know that the matrix elements of an operator, for example, are denoted as the matrix elements are of the form bra A double prime x ket A prime. Okay, and let's say that A prime, this ket A prime is an eigenket of operator A with eigenvalue A prime. Okay, now what about the matrix elements of operator A? The matrix elements of operator A can be found in the same form. This is bra A double prime. Let me write it like this. Okay, A double prime A prime. The A double prime A prime element of the matrix that represents operator A can be written as, this is the usual prescription, bra A double prime A ket A prime. Okay, but then we can use the eigenvalue equation. A acting on ket A prime is given by A prime acting on ket A prime. So I can use it here. This is bra A double prime A prime ket A prime. Now what is this? This is the eigenvalue. It's a number. So you can pull it out. It doesn't matter where you put the number. This can be written as A prime bra A double prime ket A prime. Right? And what kind of basis is this? This is an orthonormal basis, which means that if you take products of this manner, you should get delta A double prime A prime, because these are orthogonal. Right? These are orthogonal. So which means that these are actually orthonormal. So this means that if A double prime and A prime are equal, this is 1. If A double prime and A prime are not equal, this is 0. Okay, so we see that the matrix elements are of this form: A double prime A prime, the row index and the column index. This is equal to A prime delta A double prime A prime. What does this mean? This means that the matrix elements are 0 if A double prime is not equal to A prime. The matrix elements are 0 if A double prime is not equal to A prime. What is this? This is the row index and this is the column index. So this means that if the row index is not equal to the column index, then the matrix element of this operator is 0. Okay, for example, if we take A12, this will be 0. A13, A23, all will be 0. What are the non-zero terms in this matrix? These are of the form A11, A22, A33. Okay, because the Kronecker delta here says that if A double prime is not equal to A prime, then this is 0. Okay, so what we get here? We get a square matrix which is diagonal. Alright, the only non-zero elements are the diagonal elements. And what are the diagonal elements? The diagonal elements are the eigenvalues. The diagonal elements are the eigenvalues. A prime, A double prime, A triple prime, etc. All other elements in the square matrix are 0. Okay, so if we choose to represent operator A in its own basis, okay, in the basis formed by its own eigenkets, then the matrix representation of A is a diagonal matrix with eigenvalues along the diagonal. Right, with eigenvalues along the diagonal. Right, I'll repeat. If I choose to represent operator A, a Hermitian operator A, in the basis formed by its own eigenkets, okay, then what happens? Then the matrix is diagonal. It's a diagonal matrix. And what are the elements? What are the elements of this diagonal matrix? The elements of the diagonal matrix are the eigenvalues of operator A. All right, these are the eigenvalues of operator A. All right. Okay, so this gives us a way to represent operator A as a diagonal matrix. So Hermitian operators can be represented as diagonal matrix if we choose their own eigenkets as the basis. Right. Now let's look at this expansion of operator A. Operator A can be written as, okay, I've introduced two identity operators here. I've introduced two identity operators as usual. Right, and these elements, these are the matrix elements. So I can write this as A prime delta A prime A double, or A double prime A prime. The matrix elements, we saw that these are of the form A prime delta A double prime A prime. Okay, so the operator A can now be written as A is equal to sum over A double prime, sum over A prime. I've got this bra A double prime, ket A prime, and what do I have here? A prime delta A double prime A prime. Okay. Now I can carry out one summation. I can carry out the summation over A double prime. Okay, there are two summations here. I can carry out the summation over A double prime, and then the only non-zero terms in this summation are those for which A double prime is equal to A prime. So if I carry out the summation over A double prime, this becomes, okay, that summation is gone. Right, that summation is gone because the Kronecker delta picks up just one term from that summation, which is that one term, the one for which A double prime is equal to A prime. Okay, so this summation remains, sum over A prime. This so this first summation and the Kronecker delta has picked up only those terms where A double prime is equal to A prime. So this becomes get A prime, bra A prime, A prime. These are the eigenvalues. Okay, what is this? This we called as the projection operator. This we denoted as lambda A prime. So operator A can be written in a simple form now. Sum over all the eigenvalues, eigenvalue multiplied by the projection operator. Okay, so we are basically expanding the operator A as a combination of projection operators, all right, as the combination of projection operators. And what are the expansion coefficients? The expansion coefficients are the eigenvalues. Now this works, this expression works if the basis used is the eigenkets of operator A. Okay. We have been discussing the matrix representation of bras, kets, and operators. All right. So we could work. We said that bras can be represented by a row matrix. Okay. Kets can be represented by column matrix, and operators can be represented by a square matrix, n by n square matrix. Okay. So instead of working with these abstract quantities, bra, kets, and operators, we can equally well work with these representations. Okay, we can equally well work with these representations. All right. So the representation can change based on the the basis that we choose. All right. So this is in a particular basis. We are choosing a particular basis and then representing bras, kets, and operators in that basis. If we choose the basis, these elements of these matrices also will change. Okay, and we saw something important. If you want to represent an operator A, if you choose to represent an operator A by a matrix, right, by a square matrix, and if you choose the eigenkets of this operator as, if you choose the eigenkets of this operator as the basis, then this representation has a simple form. It's a diagonal matrix with the eigenvalues along the diagonal, right? With eigenvalues along the diagonal, right? It could have any number of dimensions depending on the depending on the dimensionality of the vector space that we are talking about. All right. Now we already know how to work with square matrices, column matrices, and row matrices. You have already studied this. Right? So hereafter, things are going to be easier because we can work with something that we are already familiar with. Okay. So with that, I will conclude. Thank you.